Hello everyone. Today we'll discuss about parameterizable LMS adaptive filter using DSP IP core. Myself Dhruv Thakkar and this project is from EE278 guided by Professor Cheng Chu. Before proceeding with the project, we'll discuss about various areas that are required to be covered before discussing in deep about the project. So the areas that are to be covered are: what is a filter? It is necessary to know some basics regarding filter before proceeding with the project, and then we'll discuss in brief about type of filter called FIR filter. Then we'll also introduce a new concept of filter called adaptive filtering and have a brief introduction regarding adaptive filter and show how and why this adaptive filter is important. LMS algorithm is type of algorithm that is used in adaptive filters. It is one of the easiest and still most efficient algorithm. So basically we'll discuss about the benefits of using adaptive filter and LMS algorithm altogether, describe various applications regarding the same and its implementation. So after having a brief description about the theoretical portion of the filters, we'll implement the filters in MATLAB and Quartus tools. So filters are basically the circuits that perform signal processing functions in order to remove the unwanted frequency and enhance the wanted ones, or it may also be used to do both of the functions altogether. As it can be seen here, low pass filter passes the low frequency and attenuates the high frequency, whereas the high pass filter over here passes the high frequency and attenuates the lower frequency. Similarly, a combination of both low pass filter and high pass filter that passes the frequencies in a given range and attenuates other frequencies can also be designed. This is just a very simple basic definition. The type IIR filter and FIR filter. IIR filter means infinite impulse response filters. These filters are digital filters with infinite impulse response. Unlike FIR filters, they have the feedback recursive part of filter and are known as recursive digital filters. Whereas in digital signal processing, a finite simple impulse response filter is a filter whose impulse response or response to any finite length is of so we response are feedback and hence they have finite impulse response, whereas infinite impulse response filters are filters which possesses feedback and keeps on giving infinite responses. So what do you mean by impulse response? In signal processing, the impulse response or impulse response function is its output when presented with a brief input signal called an impulse. More generally, an impulse response refers to the reaction of any dynamic system in response to some external change. In both cases, the impulse response describes the reaction of the system as a function of time as well as frequency. So, the filter that we are designing here, adaptive filter, is using an FIR filter. So, this is the basic general block diagram of an FIR filter, where here Xn is the input signal to the FIR filter, whereas the Z inverse shows the delay in the input signal, and the B multiplied input signal, and here sigma shows the basically Xn is a sample of various signals that are given at a that are passed through the FIR filter at a given added to the past as well as present signals, and we get the final output as y of n. So basically filter uses a a max circuit, that is multiply and accumulator circuit. So now we'll move to the next slide that gives an introduction to adaptive filter. So an adaptive filter is a system with a linear filter that has a transfer function controlled by various parameters and means to adjust those parameters according to an optimization algorithm. So basically, adaptive filter uses an adaptive algorithm that changing the weights that amplifier filter according to the requirements, and hence it helps in reducing the noise as well as the error signal. This optimization algorithm can be of various types. For this purpose, we are using LMS algorithm, where LMS stands for least mean square algorithm. Because of the complexity of the optimization algorithm, almost all adaptive filters are digital filters. Adaptive filters are required for some applications because parameters like input and the output desired signals may change. So we'll so it is important to know why adaptive filters are used and what is the basically need of the various problems caused because of and these problems are like subtracting noise from a received signal in one, distorting the signal if not done properly. Adaptive filters also help in leading to an increase in the level in the decreasing in hence it requires that the noise estimate should be exact replica of an. However, since these condition parts are not known and are not controlled, so we need an adaptive filter to control the noise by changing the coefficients according to our requirements. So hence the name adaptive filter as it has the coefficient of the filter according to the noise in the input signal, and hence it tries to minimize the noise in the signal and hence converts the error at the output. This shows the block diagram of an adaptive FIR filter, where this is the adaptive controller. It indirectly affects the FIR filter by changing the coefficients according to the requirements and hence reduce the noise in the output. Thus, adaptive filter helps in reducing the noise. So now, after having a brief introduction regarding what is an adaptive filter and why there is a need of using an adaptive filter in signal processing, we'll proceed further with our requirement to make an adaptive filter using algorithm called LMS algorithm, where LMS stands for least mean square algorithm. So least mean square algorithms are a class of adaptive filter used to mimic a desired filter by finding the filter coefficients that relate to producing the least mean square of the error signal. Hence, it changes the error signal according to its least mean square and helps in changing them and modifying the coefficients of the FIR filter, and hence reduces the noise exponentially. It uses a stochastic gradient descent method in that the filter is only adaptive. It was invented by a Stanford professor called Bernard Vibro in his first PhD. This shows a brief block diagram of LMS adaptive filter, where these are the weights of an FIR filter. The Xj shows the input signal, Bj means the desired signal, Y is the filtered signal obtained from Xj after the FIR filter, and the error signal is again fed back to the FIR filter, and hence it changes the coefficients of the FIR filter using the LMS algorithm. This is an advanced version of the same block diagram. This shows an architecture of LMS adaptive filter engine. This is the internal design architecture of the LMS adaptive filter engine. So basically, LMS algorithm has three major equations that help in understanding the algorithm. and implementing the adaptive FIR filter. The first equation is the Yn, where Yn stands for the output, filtered output after the action. So the Yn new is equal to Yn old, Y of n old, plus W of W new, where W stands for weight of the filter, that is the coefficient of filter, multiplied with the input signal x of n. The new weights are calculated using the old weights from the second equation, where W new is equal to W old plus mu into x of n into E of n, where x of n, as said earlier, means the input signal and E of n is the error signal, and mu is the step size. And error is calculated using d of n minus y of n, because it is always the desired minus the output signal giving us the error. Desired is the ideal signal that is expected at the output, whereas yn is the signal that is distorted with the noise from the output side. Here mu stands for the step size. The step size should be also not be too small or also not be too big, otherwise the error signal won't converge. Ideally, ideally mu means 1 by 2 raised to I beta. This is the table for a 4-tap filter. It is always assumed that initially all the input signals, desired signals and the output signals are 0, and hence the first error signal that we obtain is going to be desired minus output signal. So for a 4-tap signal, there are 5 stages. The first stage is because of the error signal we need to calculate. Here, the new weight is calculated using the old weight plus mu into error signal into x of n. As initially the error signal is equal to 0 because of the desired and output signal being 0. The W mu is also 0. So, and hence all the signals are 0 in the initial stage, but this won't be the case as we move further, and we will have the values for x, y, w, d and error. Here, as initially all the cases are assumed to be 0, all the signals are assumed to be 0, all the obtained values will be 0. But this is the basic equation that sums up all the cycles and helps in obtaining the values as and when required. Now, after having the theory discussion regarding the FIR filter, let's move to the implementation and simulation of the filter. Basically, we have used two design tools. One is the MATLAB, and second is Quartus tool. And hence, we will obtain the graphs that will show us the convergence of the error signal, and hence prove the efficiency of the LMS adaptive filter. Simulation in MATLAB that shows the signal x, where x is the input signal. Initially, it is 0, and hence after that the value of x changes. The value of signal y initially is 0, and slowly and gradually increases, and then as noise gets added to it, it kind of distorts from the signal x. As said earlier, that signal y is assumed to be 0. It is 0 over here, and slowly and gradually, as we move to the further cycles, the value of y changes. Similar goes for d, as we have assumed that d, that is the desired signal, is initially 0. There is a 0 signal over here, and hence it slowly and gradually increases, and hence changes with the increase in number of samples. Same goes for the error signal, as error signal depends on the desired signal as well as the output signal. As initially both of them are 0, so even the error signal is 0 in the initial stage at the starting samples. But as and when the y and d signal changes its value, the error signal also changes its value. Slowly and gradually it increases, but with the efficiency of the adaptive and LMS filters, the error signal keeps on slowly and gradually with the increasing number of samples. It converges, as it is seen that it converges around between the number of samples of 300 to 400, It slowly and gradually converges to zero. Similar implementation of LMS adaptive filter is done using Gorilla code in quarters 2, where here, here the upper signal is the XN signal, as it is seen that XN is the user provider signal. Here we give the value of X as our samples, number of samples, as this is the desired signal. Desired signal is 0 over here initially, as we assume all the signals initially to be 0. So desired signal is 0 here, and slowly and gradually it increases the value, and it has its own value then. Here, this is the middle signal is the error signal, as it depends on the desired and y, as we stated earlier. So as both of them are 0 initially, the ultimately error signal also is 0. But slowly and gradually, as both the values change, both the signals change their value, error signal also changes its value, and it converges. So the conclusion that we have at the end is that we gave a brief introduction to adaptive filters and LMS algorithm. Also, implementation of adaptive filter on FPGA using LMS algorithm was done. Then later on, the performed simulation results in MATLAB as well as Photos and shows the convergence of the error signal and success and shows the as well as the noise signal. Also, the step size that we mentioned has its limitation. Its range depend upon some statistical parameters of the signal. Signals with different signal-to-noise ratio were tested, and lower limit of SNR for particular value of step size and signal amplitude was determined. Future work. Basically, the adaptive filter was implemented on simulation level, which can be further developed to produce a standalone to remove real-time noise in speech signal. The figure that we have shown in the next slide, to know its implementation, that will help us to know adaptive noise canceller implementation system, where in the real time this filter runs and helps in removing the noise from the input signal that is given. This can be done by giving a reference music or a signal and adding a noise from the surroundings to it, and hence the output signal can be determined by removal of the noise and getting the same music or the signal that is given at the input. So basically using the B1 there, this is the reference noise, this is the signal noise, and hence by removing the noise or error from the signal, you can get the output. You can get the output signal that is equivalent to the input signal, and is not that much distorted. Also, future developments will also consist of creating a nearest to hardware implementation of FPGA to send the input information to serial port, and also in order to visualize the output signals. It can also be implemented on PC as it is necessary to make the digital to analog conversion. For a better precision, floating point operations can also be performed on the hardware level. These were the references that I used in order to implement this project and make this presentation. And at the last, I would like to acknowledge Professor Chang Chu for his timely suggestions and guidance that has helped us to complete this project. Thank you.